Hi everyone, welcome to this complete explainer on Class 10 Physics. So today we're doing a full chapter revision of electricity. Look, I know the pressure of board exams is very real right now, and honestly this chapter can feel a little daunting. But my goal today is to break it all down, make it super accessible, and honestly get you feeling 100% confident. We're going to lock in these fundamental concepts right now. Let's get into it.
But hey, before we jump into the heavy formulas, let me ask you a kind of fun question based on our source material. Does electricity grow on trees? Or, does it just bubble up from the ground or fall from the sky? It sounds totally absurd, right? But it really forces us to stop and think, what actually is electricity? Like, where does it even come from? We use it literally every single day, but we rarely stop to think about its physical origins. Well, to answer that, here's our roadmap for today. We're going to cover electric charge and current, conductors and insulators, electric potential difference, Ohm's law and resistance, and finally, heating effect and power. We're starting micro and building all the way up to the real world.
All right, section 1. Let's look at our very first building block, electric charge and current.
So to really understand charge, it helps to compare it to something we're totally familiar with, which is mass. Think about a physical object, like a rubber ball. The actual amount of rubber used to make that ball is its mass. It's a fundamental property. I mean, if a ball has zero mass, it just doesn't exist, right? Well, just like mass makes up physical objects, charge is an equally fundamental property that's present in literally every single atom of matter. Whether we're talking about a massive planet or a tiny little atom, they all have mass and they all have charge. Specifically, those positive charges from protons and negative charges from electrons. Now, that charge is just sitting there doing nothing. Well, nothing happens. But when it actually moves, that's when we hit our magic definition, electric current. Electric current is simply the rate of flow of charge. And specifically, in all the materials we use every single day, it's those negative charges, the electrons, that are actively flowing around. Long story short, if the charges aren't flowing, there's absolutely no current. So how do we actually measure that flow? Well, here is your first critical formula, I equals Q over T. I stands for current, Q is the total charge in coulombs, and T is time in seconds. It's basically just asking, hey, how much charge is passing through this point per second? And actually, as a quick pro tip for your exams, don't forget that total charge Q is equal to N, which is the total number of electrons, multiplied by E, the charge of a single electron. Keep that in your back pocket. Moving right along to section 2, conductors and insulators. Because if current is just moving charge, we've got to ask why it moves through some stuff and not others. Let's break down the microscopic differences here. Take a fantastic conductor like copper, right? Atomic number 29. If you look closely at its electron configuration, it's got this one lone valence electron way out in its outermost shell. Because it's so far from the nucleus, the atomic pole holding it there is super weak. That means this electron can easily detach and just roam free. But on the flip side, look at a good insulator like carbon. Its electrons are tightly packed. They are incredibly busy sharing bonds just to stay stable. They're locked in tight, so they literally can't flow, meaning zero electric current can pass through. I actually absolutely love this analogy from our source material. Free electrons in a conductor are exactly like students who just finished their final board exams. Think about it. They have zero pressure, no bonds tying them down to their desks anymore, so they are totally free to just roam the halls. In a copper wire, it's these exact carefree roaming electrons that are actually doing the heavy lifting and carrying the electric current. Okay, section 3, electric potential difference. So we know what moves, those free electrons, but what actually pushes them to start moving in the first place? Think of it this way. Imagine you have a liter of water sitting on the ground floor, and you need to get it all the way up to a rooftop water tank. That water isn't just going to flow up there magically on its own, right? It requires physical work. You actually have to install a motor to pump that water up against gravity. Well, it's the exact same principle for electricity. To move a charge from a point of low potential to a point of high potential, you have to do work. A battery essentially acts exactly like that water motor, giving the electrons that necessary push. Formally, we call this push electric potential difference, or voltage. It's defined as the work done in moving a positive charge from one point to another. The formula is V equals W over Q. So, voltage equals work divided by charge. We measure this in volts, which, and definitely pay attention to this for your numerical questions, is quite literally just joules of work per coulomb of charge. Awesome. On to section 4, Ohm's law and resistance. Now that we have the push, Let's look at the pushback. What hurdles do these electrons actually face? Before we get to the hurdles, though, we have to respect the golden rule of the chapter. Ohm's law states the electric current flowing through a conductor is directly proportional to the potential difference across its ends, assuming, of course, that physical conditions like temperature stay constant. What does that actually mean in plain English? Basically, the harder the battery pushes, the faster the charges flow. But they don't flow infinitely fast, right? And that introduces resistance, which we represent with the letter R. Resistance is basically the property of a conductor to resist or oppose the flow of charges. And from Ohm's law, we derive arguably the most famous equation in basic electronics. V equals I times R. Voltage equals current multiplied by resistance. So why does a wire resist flow in the first place? Well, imagine our free students running blindly down a super crowded hallway. What's going to happen? They bump into each other, they crash into walls, they collide with other kids. It's chaos. Inside a conductor, as these free electrons flow, they are constantly colliding with the atoms of the material. And these microscopic collisions are exactly what cause electrical resistance. All right, final section. Let's look at the real-world, macroscopic outcomes of all this invisible stuff: heating effect and power. Remember those electron collisions we literally just talked about? Well, physics tells us that work doesn't just disappear into thin air. The work done by a battery to forcefully move these electrons against that resistance gets converted directly into heat energy. This is the heating effect of electric current. It's exactly why things get warm when they run. And hey, quick safety tip, please do not go grab a glowing traditional light bulb to test this out. The heat generated is actually intense. Now, because these devices are consuming energy to create heat or light, we measure their efficiency using electric power. Electric power is simply defined as the electrical energy consumed, or the work done, per unit of time. It's basically the rate at which an appliance is using electricity to do its specific job. And for your exam prep, you absolutely need to lock these 4 essential power formulas into your memory right now. We've got power equals work over time, or P equals W over T. Power equals voltage times current, P equals VI, and if we substitute Ohm's law in there, we also get P equals I squared R, and P equals V squared over R. Depending on the exact values you're given in a numerical problem on the test, you'll need to know exactly which one of these 4 tools to pull from your toolkit. And wow, that brings us to the end of our complete physics revision. But before you go, I want to leave you with a quick thought to connect all of this back to your actual reality. Look at the very device you're watching this explainer on right now, whether it's your phone, a tablet, your laptop. Knowing what you now know about charges, voltage, current, and resistance, how much electric power do you think your device is consuming this exact second? Think about the millions of electrons colliding inside it right now just to light up your screen. Physics isn't just locked away in a textbook. It's literally happening right in front of your eyes. Keep questioning everything. Best of luck with your board exams, and I'll catch you in the next explainer.